Hey, welcome back. Today we have another mixed bag of shop talk for you, and as usual, topics are all over the place. I have a little bit on 5C backstop, the repeatability of telescoping gauges, not necessarily the precision of telescoping gauges, just looking at the real repeatability. And finally, I talk about the Multifix tool post and why I chose it for my lathe. Most of you might be familiar with depth stop that go into a 5C collet. A 5C collet has an internal thread on the end here, and you can take a depth stop that screws in the back. Those are available commercially from different sources. You can get them from Harding, for example, or you can buy a Far East import, which this one was. Screws in and gives you positive registration for your part to get kind of the same length of the parts. In reality, you don't, because these are not dead length collets, and depending on the diameter tolerance, your pull distance changes. But for medium accuracy work, they are fine. Also, they support the work against cutting pressure if you cannot clamp the part very tightly for some reason. The collet stop I have here started out as a $7.99 special from Far East. Worked fine. I turned down the end so it can go in a smaller collet. But the annoying part was the threaded section here. This is threaded relatively fine, and the ID of the stop here was threaded too. So to adjust it, you had to spin this about 2,500 times to get it end to end. So that was no good. So I took the original body of the depth stop, and then I took a shaft collar. This is an off-the-shelf shaft collar, obviously a larger one. And I relieved one side of the shaft collar and silver braced the other side on the back side of the collet stop. And this gives me a clamping situation with one screw that's very, very strong, very quick to adjust. So adjust it wherever you want and lock it, and that doesn't move anywhere. And the way I lined everything up, this is a 12mm pin, and this started out as a 10mm shaft collar. I silver braced it on. I roughly aligned it with the old screw. That's the reason why the end of the screw is turned down. I had this in here, screwed in, and the shaft collar clamped on here. Then I spot welded it with the TIG welder in 3 places, and then I silver soldered the half of the ring on here. That's why the other side is relieved. So this side of the ring still can move while this is fixed to the body here. Then I just put it in the lathe, filled the slot with shim stock, clamped it, bored and reamed it to 12mm, so I can use case hardened and ground linear shafting like this piece here as a depth stop. Usually I would use it like this, just with a flat face. Or if I need, if I want to support, for example, a large disc for drilling, what I obviously did here, because I drilled through into this screwed on disc here. This is sacrificial. Made a bunch of them at one. This just screws onto the end of the shaft piece here, and this allows good support and also sacrificial surface. So this works very, very nicely. I'm quite happy that I finally did this after about 5 years. Goes on, and you're good to go. This unscrews from the end, just a single countersunk screw, very long screw, and I drilled a little bit in the end here. This is an M4 thread, so I can also screw in thinner pilot diameters. So if I need a stop for a 3 or 4 millimeter collet, I can machine a matching insert that screws in here. Very useful, a small modification to a very inexpensive piece, and works just fine. So here's the stop in use. I placed it beforehand about 4 millimeters behind the face of the collet here. The part I'm going to face will be 5 millimeter. And then I took a boring bar, a CCMT boring bar with a steel insert, and I took a very, very minor facing pass on the backstop. That takes out any axial or radial runout, which translates in a facial runout because the face is wobbling. It's not crazy bad. It's about 0.02 millimeters of facial runout, but we can do better than that. And then I'll just drop my part in, clamp it. It's basically like a normal backstop for a 5C collet chuck, just more convenient because it's quick adjustable and you don't have to thread it a million times to move it this far. The face is flat. The other end will be drilled and tapped, so I can insert smaller diameter or bigger diameter discs as a stop. Also hollow drilled one, so the nipple from parting off a part can go in there. And here we go, 499, let's turn it 90 degrees, 499, 498, 499. So that's pretty darn good. 5 millimeter stainless disc. I need to part off about 30 to 40 of these short pieces of 5 millimeter aluminum stock. And I want to part them off very close to final length, so I have a collet stop in this 5C collet here. And I want to run the stock like this. Just part it off, take the part out, push the stock in up against the collet stop, and be quite fast that way. So this is, of course, this is not a good condition. You cannot run this at 1000 RPM and be safe. This would create a whipping situation and hit you in the forehead, probably. Or, as I heard on the With Intolerance podcast, you can't do that. It's an illegal operation. Listen to the With Intolerance podcast. It's really cool. It's really fun. Lots of great guests there. One of the recent one was Tom Lip. So what I do instead is Robin showed this years ago. I take a brass tube as a liner, as a guide for the stock. This goes in the tailstock of my lathe. Okay, and now the 5 millimeter rod is guided, relatively safe. So this goes in the chuck up against the stop. Tighten it down. Running at 1000 RPM. I'm going a little bit past the center with the parting tool to cut off the nib right away, the parting tit. Part goes out. Stock comes out the spindle liner up against the stop. Once I'm almost through the material, you see me putting some drag on the stock, and this usually breaks off the remaining material reasonably flat on the end of the stock. V-blocks. Robin talked about the issue with them in one of his videos briefly, and that's the deflection of the part by the clamping screw. When you use a V-block for work holding like this on a grinder or on a mill or whatever, or you have a V-block on a spin fixture on your surface grinder or tool grinder, and you use a single screw as usual in the center and you clamp down like this, there is a large likelihood that the part is going to deform and deflect. And what's happening there is the screw is pressing down on your part, and due to the force it gets in the area of the screw wedged down further into the V-block because it's very high load, and it's still resting out here where it was before. That means that the part goes into a banana shape. It bows like this, and Robin talked about using a spreader piece up here to negate that effect. But I want to visualize that effect, so let's bring in a dial indicator. This is a 2 micron per division dial indicator. The indicator is resting on top of this ground dowel pin, and when the needle goes right, that means the part is lifting, and when the needle goes left, that means the part is dropping. And when I tighten this clamping screw now with a cross pin and 2 fingers, watch what happens on the indicator. Nothing. So we're very close to the V-block, very close to the resting points out here, and there the effect is very minimal. But when we move out like an additional 40 millimeters like this, now we're about 40 millimeters away from the V-block, and when I tighten the V-block screw again, whoop, part moves. It bends, obviously. It goes up by about 10 microns. That's 0.01 millimeter. That's a little bit less than 0.5 of an inch. Now I have a spreader bar in here that is reasonably high, so it's reasonably stiff in vertical direction. Zeroed out the indicator, or close to it. Just watch the needle move or not move. And I'm tightening again with roughly the same torque as before. And it still moves a little bit, but it's more in the 2 to 4 micron, and I just bumped the magnetic stand. But as you can see, the spreader piece changes the behavior by a great amount. I get a deflection of maybe 2 micron now out here on the end, compared to 10 to 20 micron without the spreader piece. And the spreader piece is really just a piece of flat stock. You can make a fancy one with a small with a V-groove down here and a small dimple up here so it does center on the screw head. But usually I'm just too lazy to make something like that. So, and here again, without the spreader piece. Yeah, for precision work, that's not good. That's really bad. In this case, this is now 16 microns off center. That's a lot. That would relate to a total indicated runout of something like 38 microns. And that's a hell of a lot, especially if you're doing grinding work. So I just want to add this to Robin's video where he showed this, just to visualize the effect and just make you think about strain, contact pressure of a screw, what happens when you tighten a screw, things like that. I want to do a blind test with telescoping gauges. I use this quite a lot because I found that they give me good results. But I'm working on some relatively precise parts now, and I want to do a blind test. Usually I look at the micrometer display while I'm reading or feeling the telescoping gauge. So, and this time I want to do 10 measurements blind, take the tape off, take a reading, write it down, and then calculate the average and see how much I get deviation. And I will take 10 individual measurements on the part and check them with the micrometer. Okay, first one. I'm at the upper limit of this micrometer. Okay, that's my first reading. That's 26.503. Now we close the display back up and we give this a spin and we take a new measurement. And when I take a measurement on the telescoping gauge, I like to start small with the micrometer. Open it up slowly, and when the telescoping gauge starts to engage into the micrometer between the two anvils, I will slowly open it up more, and I will constantly change the orientation of the telescoping gauge and slowly open up. And at some point the telescoping gauge will slip between the anvils, and no matter the orientation I will not get any resistance. Then I will slowly move the anvil back in a little bit. Okay, and then I get resistance, and then I move it back. There is and then I find a very, very small amount of resistance. Okay, that's good. 26.501. Open the telescoping gauge, move the micrometer, take another measurement, and I will do this until I get 10 measurements. Okay, the way I like to use the telescoping gauges is pretty much standard what everybody does, I think. I like to compress them. So you get them in, clamp them, you go in the bore, release the spring tension, then I wiggle them first of all up and down. And that way they kind of self-center in the bore. Then I go a little bit off axis with the handle of the telescoping gauge. Then I lock it a little bit. How much you tighten this depends on your telescoping gauge. You have to try it. If you tighten this too loose, the plungers will creep out after the measurement. If you tighten this too hard, your dimensions will come out oversized because deflection when you sweep the bore diameter. Then I just do a single sweep out. Usually at the way out I give a little bit more drag on the screw here. There is no real magic to these. There are a few points. You have to get used to them, especially to the set you're using the most. You have to practice. As with every skill-based tool, you have to practice a little bit at least. Take a gauge ring or something you know the diameter a bearing race in a race, something like that, and just do measurements over and over and over and over, and also do blind tests by covering the dial or the display of your micrometer. For a rough measurement, I would even use something like calipers. This usually gives me a good ballpark dimension of the bore. These are Mitutoyo telescoping gauges. They're a little bit nicer than the €15 or $15 sets that you can get on Amazon, but even those work if you do some work to them. This old Tony did a video on them where he showed the internals and what to do to make them a little bit nicer. So that's my next measurement, 26.501. Oh, I see a pattern here already. Okay, 26.496. The problem with telescoping gauges is they require the necessary skill to pull off a decent measurement with them. Something like a 3-point internal mic doesn't need much skill. You need some training to do it properly, but once you know how to use them, they are skill independent. Not so much with the telescoping gauges. They are telescoping gauge I would consider high skill, high risk. 26.498. Yeah, okay. Let's look at the numbers. But just looking at the numbers, well, it's definitely 26, and it's definitely in the 0.4, 0.6 range. Let's try calculating the average. Divided by 10, and this gives us an average of 26.53. That's most likely completely off, because when we look at the numbers and we would do put this in a graph, we would have like, let's make a graph. These are the measurements, 1, 2, 3, 10 measurements, and we have 26.5, 26.6, 26.7. So 26.6, 20.5, sorry, 26.5, 26.5, 26.67. That's almost 26.7. 26.5, 26.5, 26.5 and a little bit, 26.5, 26.5 and 26.6. So it looks like, whoop, whoop. Most likely this and this is an offshot. It's an irregular measurement error of quite significant size. So if we take those two out of the equation and calculate our average again, 26.5 gives us an average of 25. I'm stupid. 26.503. And when I look at the numbers, I'm very certain that this is our diameter. I would definitely ditch the last digit. The micrometer I'm using is a Mitutoyo 1 micron. It has 2 micron error. That's plus minus 2 microns on the reading. So I would definitely ditch the last digit in this case, especially as it's a transfer measurement. So I'm very certain that this is 26.5, maybe plus minus 10 micron, to be on the safe side. I'm no expert in statistics. My sample size is relatively small, but taking 50, 60 measurements with telescoping gauges gets old over time. And you have to take the fatigue of the person who does the measurement into account too. So for the small test, the sample size should be okay. It's quite interesting how close they are, except for this one, which is 20 microns off. But still, interesting little test. Might be obvious, but I changed the tool post on my lathe. I used to have a Swiss Trepan 111 dovetail style tool holder on this machine, and for various reasons, which I will talk in the next few minutes about, I changed to a Multifix holder. Multifix it's originated in Switzerland, but now every man and his dog makes them. This one is AXA branded. These are made in Germany. Really nice quality, nice tooling, and reasonable, affordable. It's still a lot of money. So it's a tool post, obviously a quick change tool post with tool blocks that look like this. They have this serration here, and the tool post itself has the same serration, 40 positions. That means 360 divided by 40, every 9 degree you can insert the tool block. That means that the ID and OD tooling is the same, or the blocks basically. There are of course boring bar holders which go in like this, which can hold a boring bar or a sleeve for a Morse taper. I have a Morse taper 2 sleeve for drill chuck or drills, or you could even put a grinding spindle in one of these. 30 millimeters is a lot of meat to work with. Yes, it's basically standard here in Germany or probably parts of Europe on industrial lathes. There are not much alternative. Parade makes a tool holder that's also dovetail style, but apart from that, in the Trepan, it's basically all Multifix. That's almost standard. A is the size. It's this one. There is one size smaller, AA, and up they go to something like C or even larger. We need basically a crane to change the tooling. At work we have a Shoptalk 135 lathe, and we run it with a Multifix B, next size up, which is basically 1/3 larger, or almost like this. So I had to take some minor modifications to my solid tool post to be able to put the Multifix A on here. Not too big of a deal. It's pinned in place with 2 pins and located near our central dome. This large post here in the center, 60mm hardened rod, which is basically the nut which holds the tool post in place. This is also again my mounting point for an indicator. And you can use the boring bar holders just as the other tooling blocks in every orientation that you want, which gives a lot of options. And that's one of the main reasons that I switched from the trepan to this system. The trepan is an excellent system, no doubt about it. It's very accurate, well made usually, very repeatable, which this one is too. And it's a simple system with the dovetails. The tooling blocks are easy to make yourself. The problem is, you either have to buy the tooling blocks in Switzerland, these parts. They are like 120 euros a piece, which is a lot of money. Or you make them yourself, and I resorted to making them myself most of the time because it was a hobby and I had time to do it. Now that I run this mostly as a business, I don't have that much time anymore to work on personal projects, to be honest. I work the most of the time on customer parts or fixtures to make customer parts. So very little time to mill something as simple as a tooling block for the quick change tool post. That was basically one of the two main reasons. The price and availability. The other reason is a trepan tool holder, the base tool holder looks like this. It's angled. That means, and it's mounted in a way that this is oriented with the cross slide travel. You have your straight tool holders mostly for OD work like this, and you have these angled blocks which are for ID work, oriented like this. You have them probably seen in my videos a million times. All these are made myself. So the problem is, once you make a block, either an ID or OD one, you're committed to it. This isn't. It's very hard to use this for OD work. You can with a left-handed tool, but it doesn't always work. So basically, I have about half of my tool holders are ID holders, and the other half is OD holders. I have some specials like the drill chuck or parting holder. That's a different story. But with those, you're committed. And if I need now, like for a certain job, like 15 OD holders for some weird reason, well, that's a problem. I don't have those. With the Multifix, every OD holder can also be used as an ID holder. Or, if I need to, as an angled holder, which can also have uses. Not very often, but can be useful. So that's the other main reason, just flexibility. Each tool holder can do everything here. Within its overall shape, of course. This will not hold square 6mm tooling. But I have some ideas for these large 30mm holders apart from boring bars. For one, a grinding spindle. And second, a even more compact rotary birch than I already have, that goes directly in one of those holders. This is the Hemingway rotary birch that I made years ago. Works excellent and goes in the tailstock. But tailstock is so 2000, and we are in 2020, so wouldn't it be nice to have a rotary birch that sits fully engaged in such a holder? Just an idea, just playing around with ideas, and make it more heavy duty, make it with needle bearings, needle roller bearings and needle axial bearings, make it really heavy duty, go in here and you're rocking. Make a holder for these, for rotor broaches, so you can power feed them. Just some ideas what I want to do with the system. And the nice thing is, if I need an external holder, I can buy one. I can just, they're readily available. AXA in Germany makes them. Pivot Tool is an importer which sells these made in Far East. He seems to have reasonably good quality control. And many other places. And also there is a huge second-hand market for these. If you go to a used machinery dealer, usually they have these at hand. If you buy one from AXA, they are around 50 to 60 euros. One. Compared to a 3-pound holder, which is 120 euros, that's a pretty good deal. The teeth on the AXA ones, these are ground. If I had to guess, these are profile ground with a dressed wheel that has the contour in it in one pass. A friend of mine has wire EDM. He cut a bunch of them on the wire EDM. That works also quite nice. Looks really good. The PV Tool ones, which he has made in Far East, are also wire cut. Problem with wire cutting is the surface roughness. If you don't do enough skimming passes, the surface roughness is quite high. So the slidability of the Multifix, of the ground ones, is quite nice. These go in really cool. Locks via an eccentric bolt back here. Height adjustment is with this screw here and this counter screw. Using the same square drive wrench for both the clamping screws down here and also for this lock nut. Okay, a little throwback in time. Here I'm machining down my solid tool post using a fairly small carbide end mill, but this allows me to take a quite aggressive cut and buzz off that material quite quickly. I'm using the mill with a 10mm tool in here that centers on the Multifix tool post. I'm using that to figure out the position of the tool post on my solid tool post mount. And I touched off on this side and this side of an edge finder, and now I'm just moving the axis around to position it nicely. In this direction, I'm just going with the end of the tool holder flush with the block here. And in this direction, I'm going a bit further back than I had the trepan, because I want the center of the tool, where the cutting action, the cutting force goes down into the cross slide and then into the bed slide or the carriage. I want that to be a little bit more to the center of the carriage, not as far out as I had it with the trepan. So this is probably it. This is probably the position I'm going to put it. So this is cast iron. So we're going for about 1.5 times diameter thread engagement. It's a 10mm thread, so we're going to make the thread a third 15mm long. So the thread needs a little bit longer, something like 20mm because of the lead-in on the tab, and we need to drill even a bit more deep to have clearance. There we go, that's 25mm deep. If we can trust the internet, the impossible task, tapping with a keyless chuck, touching off the depth with a scale. Okay, you saw me milling down the solid tool post about 7 millimeters. I surface ground the top, and then I drilled the holes for the dowel pins. There are extra holes here and here, because I assumed that the orientation of the holes matches to the orientation of the teeth, but in hindsight, that's not... how would you do that? You would need a fixture that aligns them. And in reality, they probably just hold it like this in something like a large collet and drill those two holes. Maybe even before they cut the teeth. That means the orientation between the holes and the teeth is not existent. And with those two holes, my tool post was off, and I could not adjust it by slightly moving the solid tool post around. So that was no good. So I decided to drill 2 more holes. And this time I used the tool post as a drill bushing. I put it on here. This was mounted and aligned. I put the Multifix holder on here, and I had a boring bar holder with a piece of round stock in here that I used to align the Multifix by turning it, running an indicator along. Then I bolted it finally down. Then I took the whole solid tool post off, still with the Multifix mounted. I took a 6 millimeter dowel. I aligned each of the holes on the mill. Then I drilled and reamed them 6 millimeter, 6H7. Put the pins in, turned a new post with 20 millimeter, which is this diameter here. And as you can see, that's the fit I was after. And the alignment, when I put this all together and put the tool post on, a block on it, is pretty darn good. So let's put this together. We have the clamping band. This goes around like this. And we have this piece. This is the marker for the rotation. Here is the washer with the pointer on it. Let's see, this goes on like this. Now we need a tool holder, like this. Then we align this pointer with the 0 mark. This is just a help. And then we put the nut on. In this case, it's not a nut. It's a piece of 16 millimeter case hardened and ground linear shaft, which allows me to use my indicators on here. Take our adjustable wrench. Has a flat ground on here. Tighten it down pretty good. And we're ready to go. Multifix wrench. There we go. Okay, that's all I got for now. I hope I was able to assemble a kind of interesting collection of topics. The project I'm working on currently are of the kind that I'm not allowed to share, so I have to improvise a little bit. Thanks to all who support me, those who support me on Patreon, those who obviously watch my videos, those who comment. So thank you all, and stay safe, be kind to each other, and I'll be back.